Okay. So it's just quite a detail.
Ungada is speak something.
So good morning, everyone. Welcome to our workshop, Teams workshop on spatial geometry in module forms. And we will have 4 days program consisting of 4 mini courses delivered by 4 organizers. And then we have a few invited talks. So before we start, I would like to thank our team's director, Professor Zheng Daoyu, to welcome everybody to say a few words.
So on behalf of the team's assignment of the chairman of the teams, and so I would like to welcome everyone to join this wonderful conference. So I guess the purpose of this conference is not just for bringing experts to here, but also to present our PhD students. So this time we will have our actually 3 PhD students also as speakers for this conference. Okay, so I will be also with the chairman
So I'm Martin Geston, one of the organizers. I'm very happy to come to this conference at TIMS because I started visiting TIMS more than 10 years ago, and 15 years ago. It was a wonder show looking here at TIMS. So I'm happy to come back to TIMS. Anyway, the first speaker is Professor Shinobu Hosono from Gakushuin University in Tokyo, who is my former neighbor university. So I'm very happy to introduce Professor Hosono to give us this talk.
Thank you very much. Thank you very much. And thank you very much for invitation, inviting me to this wonderful workshop. Although my name is listed on one of the organizers, but mostly organized by Jin Run and Beijing secretaries. And I'd like to thank for arrangement for everything. Thank you very much. So actually, this is my last time I visited this university was I think 2014. It's long ago, and coming here is always very my pleasure coming here. It's a very nice place. So today, I'm going to have 2 talks, and one talk mostly related to mirror symmetry and looking back with some new insight and looking back the old history, and I'd like to point out something new directions or I'm trying to extend our pictures. So very briefly, the first talk, I'm going to talk about toric, Calabi-Yau complete intersection are mostly hypersurfaces in toric varieties. So this is more or less from the beginning, very historical thing, but I'd like to emphasize one point. So in any case, that's first talk. And second talk is I try to extend the construction mirror, Calabi-Yau manifold to non-toric case, and special Calabi-Yau, so which has abelian fibration structure, and how we can see the mirror symmetry. So for me, I'm trying to see the details, such a non-toric case, that there seems to be many works I have to solve. Still, I have not come to the conclusion and many exciting results. In any case, that's a second talk. So let me start somehow historical, but I hope some new viewpoint, introducing some viewpoint on the history of the mirror symmetry. So, but let me first define the Calabi-Yau manifold. X is Calabi-Yau, mostly my talk is Calabi-Yau threefold. Calabi-Yau threefold is just as a definition, smooth and projective, and canonical boundary is trivial, and the Hodge number is OX equals 0, I equal 1, 2. So my focus is just threefold. So if we, some part of results should be extended to fourfold or higher dimensional case, but I'm not sure how extended structure will be extended. So in any case, given a Calabi-Yau threefold, so what we usually see is the so-called A structure and B structure. The A structure, so given a Calabi-Yau manifold, threefold, then we have even Hodge decomposition in something like this. This does not fit into the board in the H3 and 3. And so this usually we call the H even over X. So where we see the Hard-Lefset theorem. So Hard-Lefset theorem formulated some action, so SL2C action on the entire Hodge decomposition or Hodge diagram or Hodge cohomologies. But just look at the even part, diagonal part, still this action closes among this part. And this is and the point is that this gives us certain nilpotent action. This is one structure I will focus on. And for simplicity in my talk, just the kappa is Kela class. So I assume Kela cone is, this is sitting inside one of XR. And just for simplicity, I will assume this is kappa S. Simplicial. So kappa 1 to kappa S is the generator of the simplicial Kela cone. So this is very strong condition, but not so essential, just for simplicity. And take a general element kappa for the Kela class, and then I will consider the kappa 1 plus general linear combination kappa S. And then this gives us the nilpotent action on the H-even cohomology. And on the other hand, so as you know, there is another very similar structure which is often called the B structure. This structure, compared to this structure, it's rather hard to formulate. So first thing is consider the family of Calabi-Yau. So not just single Calabi-Yau, but the formation family of Calabi-Yau. And you know that there are a lot of famous results, and there's no obstruction to make a family or those kind of things. But the global structure of family, so that part is not studied, not known so much. So in case, assume we have a family, and then associated to this family, we have the local system R pi star of 3 of. This defines local system, and associated to this local system, we have the homomorphic vector bundle, sometimes Hodge vector bundle, something. So mostly, as an element of section, we usually recognize the period integrals for the family. That's the way we often see in the context of mirror symmetry. So in any case, suppose we have a family, and given family, we have this local system. And the assumption, this is a rather strong assumption, is that this local system has a parameter space over this local system. It has a certain nice compactification where the certain special distinguished point, boundary point, so something like this, D1 to DR. So this is just, the open, maybe quasi-projective as a parameter space, quasi-projective space. And just extend the definitions, and suppose we have a certain compactification of the parameter space where we see where we see normal crossing boundary divisors, and then normal crossing point as a normal crossing point, as a special distinguished point, boundary point, which I denote O. And then in such a situation, we have monodromy transaction around the boundary divisors. That's I described T1 to TR. And then here is assumed. This is not always the case, but I'm going to show that the toric, hypersurface or completeness section, so there is nice structure. Because of nice structure, this kind of compactification and boundary point, that's what we can expect, and actually they exist. And that's the entire picture. So in any case, assume T1, TR, thus appeared. Monodromy action is unipotent. Then what we can say is because unipotent is Tk minus identity of certain power equals 0. Because of this property, we can take a logarithm of this unipotent action, and which result in the nilpotent. This is unipotent, this is nilpotent, and then take a general linear combination of this nilpotent action, logarithm of Ti, and take log Ti, and with general parameters, and maybe lambda I is positive, and then summation I, and I defined in lambda. So because this is normal crossings, and these nilpotent matrices commute each other, and then this general linear combination makes sense, and gives us a nilpotent matrix action on H3 of certain base point Q. So symbolically, I describe this acts on the this acts on the H3 of XP0 of Q, and so that this assumption is continuous. So this, I assume this nilpotent, and it naturally gives us it is unipotent, and it naturally gives us nilpotent action, which is acting on this middle dimensional cohomology space. And And the final assumption is that this action gives us the so-called monodromy weight filtration has a form, having the form something like this, O and W6. W6 is H3 of XB0 of Q. Okay. And then, so this action is, how to say, nilpotent action. So orbital decomposition we can make up. So make up the Jordan decomposition of this nilpotent action on this linear space gives us natural, decompositions. So orbital structure, something like this, and something like this, something like this. Depends on dimension. So the point is that we have naturally, this is by definition Kähler class. This naturally gives us nilpotent action. So maybe part of the SL Lefschetz SL to C action. And this gives us also nilpotent action. So mirror symmetry somehow related to this definition in this context. So that B structure, extracting B structure is rather hard part, but in any case, so definition is that the X is mirror of X star. So if so this is the definition. If exists family of this star mirror Calabi-Yau over some parameter space, just as described over there, and I assume exist continuous conditions. This parameter space has nice compactification described here, where we find boundary points, special boundary points. And this I need to get use this blackboard. I'll continue this one to here, such that H even cohomology H maybe Q in the Lefschetz action. So even cohomology. So actually, Hodge decomposition over C, but this is Kähler class is real cohomology class, and so we may restrict the R real maybe just also even more over Z we can restrict. So it's just to match both sides over Q. I write here, describe here, and the right hand side is H3 of XB0 over Q naturally Q, and then nilpotent action, and then so what I require family and special boundary point where we extract this side. The one side we have naturally Lefschetz SL2C nilpotent actions, and right hand side is from the family. Mirror side we have nilpotent action, and over R or maybe Q. So it's not such that this is. Sorry. Such that. These nilpotent, so these nilpotent actions are conjugated. But maybe I should write temporarily right here. So I usually use R. So right here. So equivalence, by this is not just the vector space, but also these nilpotent actions are conjugated to each other. This is the phi Q I wrote here. So what is that the condition is that not only Q, but there is the natural integral structure coming from the, that the actually even cohomology part, this diagonal part comes from the K group. So usually you know that the, it's taking, Z module of the vector bundles, and they take Chan characters and gives up to here. So namely, this is over Q, but from this by Chan map, we have a certain integral structure. Furthermore, in dimension 3, there is natural Riemann-Roch pairing. So this dimension odd. So this is anti-symmetric, skew-symmetric pairing here. This side is just over Q, but there is the naturally B0 of Z, and this is standard Poincare pairing. And this again, odd dimension, this Poincare pairing is the anti-symmetric. And then claim is that this is not only these two nilpotent actions, not only the conjugated, but also the condition is that this are compatible with these two integral structure. That's the definition of the mirror symmetry. Sorry, I continue this slide.
Do you assume kappa is a rational class or integral class?
At this point, yeah, rational is okay. Rational is okay here. Yeah. But I do not assume integral class. So this side in lambda is over Q. So to match this isomorphism, kappa is rational. Yeah.
The specification on the B side of the C lambda cancel out on the right side. We have extra freedom of B side lambda.
Lambda. Yeah. Sorry. So when things, sorry, I haven't prepared so carefully with some identification, with some linear identification. Kappa I to lambda I. So I will come to the case. I will explain it actually kappa I equal minus lambda I. So this kind of relation. Sorry, I haven't explained this part.
Sorry, I want to kappa is a rational class or?
Kappa is a rational class. Rational. Yeah. Sorry, I took time. I will speed up. Okay. I think, this part I haven't mentioned so clearly, but some identification I will show soon later. This is how to say? These days we have lots of versions of mirror symmetry, but this is more or less.
So you will really consider also some lambda I to be 0. Including the boundary cases.
I assume kappa positive, and this corresponds to the inside K-Lacan. So annoying thing is the minus sign is just inside K-Lacan or the opposite side. This part is that I think that's a kind of problem of identification. Now let me go to the concrete example. This side is more or less conceptual thing. So most difficult thing is you recognize the A structure is just a part of a hard-Lifshitz theorem, so no problem at all. So the B structure side, there are lots of assumptions. I assume the families and the suitable compactification where we can identify special, the boundary point given as normal crossing boundary divisors. So this is a really non-trivial part. But nevertheless, if you look at the history of mirror symmetry, then the hypersurface in toric varieties satisfies, gives us naturally these compactifications. That's the point. And then I'll continue. That compactification naturally gives us this identification, this isomer is compatible with this integral structure. So let me describe very briefly. So I'm not going into details. The NR, the pair of reflexive ortho. So M and N is certain lattice of rank of dimension. I'm focused on Calabi-Yau threefold, so I always assume this rank of lattice M and N is rank 4, into 4. And then there's the notion of reflexive polytope. And then given a reflexive polytope, then for this side, I define the summation B mu, V mu, mu belongs to the delta inside M. So just polytope something like this, and this is the delta, and then because of reflexive polytope, in an integral point is just 1 point, the origin, and then the mu1, 2, and so on. Then gives us a certain Roland polynomial associated to that. And for this side, the other side, I define the summation u and the delta star and nu, nu. So I'll focus. I'm going to details the moduli of this hypersurface. This side I denote more explicitly u1 and all the way mu p, u p. So I'm not writing precise picture, but the same thing, delta star, and then mu1 and mu2, and so on, and then mu p, and this side, and mu0. That's my notation. And with AI to A naught to AP is the I use notation both way. A nu is just the refers to integral points, but for each integral point numbered by 0 to p. So both notation I will use, and sorry, it's noticed. So the result all days 93 is that given reflexive polytope, we can associate to them, we can consider the Roland polynomial G and F with generic parameters A and B, like this. And then we consider for general parameter B, we consider 0 is sitting inside the P delta, and also FA equals 0 sitting inside the P delta toric varieties. Given polytope, we can consider, we can describe toric varieties. That's I denote P delta, P delta star, and but in general, these toric varieties are singular. Even if we take a parameter AI, A and B is generic parameters, so that means we do not have a singularity coming from this defining equation. But the singularity comes from the ambient space. But the point is that Butler found that if we take the so-called maximal projective Crepant partial resolution, then these two hypersurfaces gives us smooth Calabi-Yau hypersurface. That if you take MCP, this is a MPCP, maximal projective crepant partial resolution, then these two are smooth Calabi-Yau threefold hypersurface, and which is mirror topological mirror. So that's the historical results, so folklore results, so all this. And the point is that my focus is that I'm not going to write what the topological mirror means, but just exchange Hodge numbers. And I want to see much more structure, the isomorphism. So if this definition satisfies mirror symmetry, this relation satisfies, then this deformation space sitting here, and this side is Kähler cone sitting here. These numbers are exchanged, must be exchanged. That's a topological mirror. And my focus is that this topological mirror is whether this topological mirror is actually the mirror in the sense of the nilpotent action. That's my focus today or next talk. So I'm not using Blackboard so efficiently. Sorry. So in any case, so to do that, what I do is for this side, I will consider the family of Calabi-Yau, in this case hypersurfaces, and then consider compactification and also the boundary point. And then in the end, I want to figure out how this correspondence comes out. That's what I'm going to do. So first thing is MF. I will describe the modular space of this hypersurface. So I mu, u nu, and projectified, and nu is C plus 1. So I'm using this bracket notation, just projectify, and then look only this coefficient part. So just a projective space of dimension P. So by this notation, just over here, P plus 1 are affine parameters, and then just projectify. That's a very fast step to describe the modular space of this hypersurface. But that there's a natural action, so coming from actually torus acts on the home of NC star. So by definition of toric varieties, for this toric variety, there is natural torus action here, and then this torus action naturally induces to the coefficients. So namely, given T, and then I suppose U mu is T mu times U mu. So I hope from this notation you can see this is home, or just identify this is C star of in this case dimension 4, and then the natural way this torus acts on the coordinate ring for Laurent polynomial U1 to U4, like this. And then take a quotient. So that's a natural. This acts on the ambient space, but we may translate to the coefficient functions. So this induces to mu goes to the t times mu mu. So under this action, we have to take quotient. So that's a quotient, natural definition. And then, so actually, so there is, I projectified here. So actually, this is T bar. So I removed this projectified to just CP plus 1. So because of that, T bar is C star cross T. So I define just a notation. So this is this additional C star is scaling, overall scaling of FA. So that I think this makes sense, right? And then what you know is GIT quotient. This is just abelian quotient. We can make up the quotient natural way. There is a simple way. And what I do is consider the lattice Z plus 1. I'll explain. I'll give the meaning of each term. So I define n bar. So n equal just lattice, the rank 4 lattice. So but you may think n equal isomorphic to Z4. But let me write in this way. Then I'll make a sequence like this: 1 and 0, and 1 and mu1, and 1 and mu2, and so on, all the way to the mu p. And this gives us p plus 1 column. So there's a natural map, and then I denote the kernel with L, and this is the exact sequence. So this is quite a natural setting for the GIT quotient. So because if I put A0, A1, A2, and also P here, and then the 0, 1 is the weight of this parameter A0. So A2 and all the way. So I mean the group structure is if you look at this each row vectors, this component is C star and C star and all the way C star. And this C star part is T, and this first C star is everything is 1, 1, 1, 1, 1 because of scaling. So just describing the character or representation of this T bar. So by this matrix, so we have A0 to AP, so and then just writing the weight or character of this torus acting on this variable 1, 0, 0 and this variable 1, mu1 because I said the action of this parameter is something like this. Okay, and then now it's very clear. So this side is just affine. It's an additive way writing every Laurent polynomial. It's just correspondence. And then the sitting inside here, we have the. Sorry. I have to continue this side. So this side we have the p plus 1 positive. So you recognize this is the polynomial part of sitting inside the Laurent polynomial ring. So just additively, everything additively writing to write this sequence. And then this part maps to the, I just write figure something like this. Some cone gives us cone. Oops, sorry. Just some cone. This cone is written inside the n bar tensor R. Okay. I hope this makes you can read this. And then this is the so-called GIT cone, or GIT fan. If we around here is the origin, 1,0 here, and this one is 1, mu1, and this is 1, mu2, and so on, 1, mu3. So every column vector is mapped here, so as an image of this positive cone. And then this simply gives us the GIT cone. So just simply, so in terms of Laurent polynomial and as a subring, the polynomial ring, and then this cone represents each monomial in polynomial ring, how the weight of this element. And then this L is the kernel. So kernel means invariant polynomial. That's what we need. So this is a fitting, I mean, you know the GIT quotient. So in any case, take a chi inside the GIT cone, then this gives us linearization of the quotient. Then the point is that define R chi is positive. The positive, and then AM sitting inside C, A, and as I described over there, I erased here, over here it's remained. So and torus acts on these parameters, and then the requirement is D times AM, and as a C vector space. And consider, and then the all degree. So this introduces, so fix the characters, then we can define this kind of, I mean, this is an element, polynomial ring, sitting here, and the map to here, and they take in the chi direction, it gives us and the all element aligned in the chi direction satisfy this kind of properties. And then this so-called gives us linearization of in the context of GIT quotient. So in any case, the GIT quotient is take a just project of R chi. This is a definition of GIT quotient, right? And this standard way to write this quotient is the chi of T star. This is a definition. I think I described very briefly a sketchy description of the definition of GIT quotient, how we can apply quotient here. And then let me come to the result. So you know that when we study GIT quotient, then depending on the choice of chi, we often encounter wall crossing phenomena. That comes from we divide this cone into fan, several small fans, and the wall structure we can introduce, and then depending on that locus where we choose as a linearization chi, this quotient changes. But the point here, I'm not going to describe details, but by standard, or I mean, by toric geometry, in toric geometry, people studied the following things. Then when we take chi as a linearization, and everywhere, GIT fan, as I said, depending on the choice of the location of chi, that quotient changes. But MF quotient is non-trivial. Non-trivial. So, and we have always this Abelian quotient. This gives us toric varieties, and actually there is secondary. This side depends on chi, but this always gives a toric partial resolution, where secondary sec is secondary fun. Here, the sec is sec delta star is secondary. So that's a result I'm not going to show. So secondary fun is just I think you had secondary fun, or you used probably very heavily the secondary fun or secondary polytope. In any case, in this diagram, secondary polytope is sitting inside. So here, so parameterized triangulation. So this polytope is this side. This part is the 1 comma delta, the polytope, and then there are lots of triangulation. So just look at this side, and then something like this. Many triangulation we have, or something non-trivial triangulation. I look at this kind of triangulation, PK. This is origin, and this is it's just projected to mu1, mu2, mu3, and so on, and up. And this is a polytope delta star. And then just combinatorial things. Think about all possible triangulation. Actually, regular, so-called regular triangulation, we will end up with a certain cone structure from there. And I skipped the definition of this one, but everything combinatorial. So look at these triangulations, and you can describe these partitions. And actually, this polytope sit inside this scalar extension of this kernel. This is secondary polytope. And the point is that, as I said, choice of chi, and depends on choice of chi, the quotient, GIT quotient changes, but because of this structure in this context, so every toric varieties or GIT quotient has the partial toric resolution described by the secondary polytope. That's the result in toric geometry. So now a lot of good textbook on toric geometries, and then you can recognize this statement. That's here. So in any case, this is a side for the compactification. So and here, so in this setting, but with mirror symmetry, there is natural compactification of the parameter space. Natural parameter space, because hypersurface. So we have natural definition of parameter space. And then in this case, very nicely, we also have at the same time natural compactification with this structure. Now, this part I'd like to skip. Oda Park, old days, Birela, Hillman, and Stillman. It's around late 80s, so old days, result in old days. How to say, so secondary polytope appears quite different context. Secondary fun, so-called normal fun of secondary polytope. So something like this. This N stands for normal fun. So normal fun is, I'm not going to describe normal fun, but very naively, normal fun is put the vertex here and write this kind of diagram. This is a definition, very naive definition of normal fun. So precise definition, I mean, take a vertex and dual or something like something, and dual cone and the collection of dual cone gives us normal fun. But in any case, this is right. Naive definition is this one, normal fun. So normal fun is the cone of piecewise linear functions on the fun delta fun. So around here, everything is many things becomes confusing. So delta star, just let me explain. Over there, I described something like this. This delta star is sitting 0. And then look at each phase. We construct the fun something. We will have a fun something like this. So this is a normal fun. I mean notation, not normal fun. This is the sigma notation sigma delta star. They make a cone. I mean they make a cone and then construct a collection of cone as a fun. And that's the fun sigma delta star. And then given such a fun, there is a notion of piecewise and piecewise linear function we can consider, and piecewise linear function, and it's like this. And then this gives us the so-called, I mean, the normal fun of the same I mean, polytope, secondary polytope, and the normal fun associated to that polytope. It's completely different context. So one way to use is to describe in this setting a modular space of the parameter space of hypersurfaces. And this side is completely different, something complex piecewise linear functions. And then the meaning of this one is just there is some special cone. I denote sigma naught, and then inside piecewise linear cones of piecewise linear functions, and there is the special cone is so-called strongly convex piecewise linear functions on sigma delta star. Still does not make sense so much. So very special piecewise linear function and with some convexity properties. And then actually this in terms of toric geometry, this is identified ample cone of toric variety associated to this fun. And actually this toric variety associated to this one is P delta hat. So this side is completely different. Mirror side, this side, structure of this side appears. So in this hypersurface case, this old result. And the one side is GIT quotient context, and the secondary polytope appears. And this side, I haven't went into the details, but some piecewise linear function over the sum cone. Everything combinatorial interests people studied. And then in terms of toric geometry, a special cone inside the piecewise linear function, cones of piecewise linear functions has a meaning as an ample cone of the toric variety, which is exactly the mirror side, Batiev mirror side. That's the result. Now, I come to the maybe should I? Yeah, maybe I think I can skip this. Erase this one.
So you are saying the secondary band can simultaneously describe the B model of this MF and also the A model, of the mirror side.
Yeah.
So it created the simultaneous.
Simultaneously. Yeah, this is a lucky case. My point I want to stress, that all these are historical things, so I want to stress, so in history of mirror symmetry, at the very beginning, lots of interesting things and beautiful result comes out that we can trace to this duality and the twofold meaning of secondary Polytope. So that means beyond the toric varieties, no such a nice property. That's the problem I have been encountered these days. So that's related to the second talk on my talk, second part of my talk.
You mean once you don't have the secondary band? What?
Non-toric, yeah. So, not toric in this picture, toric hypersurface or complete intersection in toric varieties is very special. So once we go outside, beyond that, then this kind of machinery doesn't work, doesn't apply literally, and we have to work out the suitable definition of modular space and the compactification and where is boundary point. That's the focus of my talk. So in case observation around 93 and 95, so we made is that the twofold meaning because of that. So associated to the special cone UT0 is xc of sigma T0 sig there. This the affine. The same cone, the project over there, the secondary projective variety described by secondary Polytope. By construction, if you look at this normal form also appears in description, but in this context, so describing a certain affine chart of P secondary data star. That means there's some affine chart, and if we take the basis L1 to R, this basis of this semi-group, check over here. Then so just following the description of the toric varieties, and then the affine coordinate is A0 L1 and all the way XR equal ALR. And then there is, so by toric compactification by toric geometries, and then toric deep boundary divisors, normal crossing, and then we can find out certain boundary point very naturally, starting from this cone. So that's one way. And then dual side is sigma T0, as I described. It's in this context, ample cone of P delta. And what we need is a Kähler cone or ample cone of the hypersurface. And this is ample cone of toric varieties, and very case by case amplicon of xg. Xg, I mean the GB equals 0, setting inside the toric variety. Right. And the amplicon is dual of the holomorphic curves inside toric varieties, and so we go to the hypersurface, and the dual of the holomorphic curves, rational curves sitting inside the xg. So there is a chance the K amplicon becomes larger, right? If we consider hypersurface, but case by case. So just assume that this part is almost equal, and then we have the.
Yeah, I agree with a friend that has studied this jumping at one point long time ago. We have contact examples. So the latches could be fail.
I see. I see. So this part. So how differs these two cones is there is an expert. We have to we can ask. So case by case.
But usually it's okay.
No, that's okay. And then kappa r and sigma t0 as a generator of this cone. So kappa 1 to kappa r is just again assuming for simplicity this is simplicial cone.
But as far as I remember, in this case it's okay.
It's okay.
Once you start with a funnel, ambient funnel to cut then in that case I guess
it's just okay. I just to be careful, I just wrote here that I had some expert on algebraic geometry, so not so big difference, and then the case by case we can work out. So in any case, there is a duality, the affine coordinate, so L1 to LR, so it comes from the dual of this one, describing the affine chart of the compactification, and this side is the amplicon. That's a duality. Now I'm going to maybe so many blackboards, so I use this. Now I come to the definition. So using the recognizing dualities, the I central charge, the formula. So in this context, from the beginning of the mirror symmetry, this kind of duality structure and quite often appeared, and then in that context, I come to this formula. That's all this omega naught 2 pi I. Kappa defines summation in ZR positive, and so here P gamma and plus 2 pi I kappa LK. So I do not use precise definitions, just this certain gamma series, gamma function. Defines 2 pi I kappa. So using that dualities, and then naturally we can write down the certain gamma series. And this actually comes from the, I'm skipping the details part, but this came from the differential equation satisfied the period integral for the family parameterized over this mosaic space in F. And then looking at the detailed structures, and I noticed that this structure summarized into a single formula. This is a central charge I called cohomology valued hypergeometric series, and then probably for simplicity central charge formula. The versus to this later generalized to gamma class, and in the context of to encode Fano varieties and all other things. But the Calabi-Yau setting, I came to this definition. And then remark, so I'm focusing on the threefold. Xg of Q is generated because of threefold, kappa 1 and kappa R. So kappa 1 to kappa R is just generator for the ample cone, the hypersurface. And then this does not generate, in higher dimension, these two, generators or ample cone, not generate the entire cohomology class. But in case of threefold H and 1 and 1, 1 and H2, 2 and H3 of 1, and then this is a Lefschetz action. And so by Lefschetz action, one orbit is something like this, and the other orbit is something like this. So 1, 1 and 2, 2 are isomorphic all the time. And then from here to here by Lefschetz action, we can move to here. That means all these elements generate entire cohomology, even cohomology. That's somehow restriction, because I'm restricting threefold. In fourfold, I don't know. I think some case by case we have to study. And that means this central charge formula, how it is nice in case of higher dimension, for example, fourfold case. I don't know so much about this. So conjecture is that this part is conjecture. Take an integral symplectic basis. So which I denote 1 and I into J of B3. So that means over H even and bracket. So I'm just focus on this even cohomology part, and then I say this even cohomology generated by the generator of ample cone, and then take a certain suitable symplectic basis with respect to this pairing. It comes from Riemann-Roch pairing with respect to A and B. I define integral xg of A star and B and the xg. So you recognize this pairing comes from Riemann-Roch, which I described at the very beginning. And set omega naught x to pi I kappa equal f0 1 plus f summation I over phi over ei 1 s summation j f2 j b2 j plus f3 b3, and this coefficient f is certain hypergeometric functions with respect to x, and then conjecture is that the coefficient functions f3 is integral symplectic basis of local system, which I described at the very beginning in general setting, Cx star of m f maybe bar. that's the, I mean, based on many calculations, all this I come to these conjectures. And, I think everything. I mean, at the very beginning, I described very, I mean, general pictures in terms of notation, and then I can describe the toric hypersurface case, very special case, and as children pointed out, the point is here, twofold meaning for the secondary polytope. In this case, very lucky because of that, and these dualities we can recognize, and then also they make this kind of special gamma series here, and then we can extract the integral structure from one side to the integral structure the other side. This is the conjecture. I haven't proved yet, so I mean I don't know how to prove, but I experienced lots of examples. There's no counter example about this claim. Now I come to I can finish. Now I come to the final part, conclusion part. The meaning. So what's the meaning of this central charge? So more or less, I'm looking back at the history, and then I'm trying to extract why it's so beautiful in case of toric varieties case. And then what I want to do is want to go.
Is this already known in toric?
This is just conjecture.
No. So this is very general calculation. Without any assumption.
Not as, material mirror, 3 dimension, 4.
But you mean even for toric, it's not good.
Yeah, it's a hypersurface or complete intersection, Calabi-Yau in toric varieties. Not proved. Some young people, in local mirror case, this conjecture, some young people said he proved, but I couldn't understand. So I can tell later. No, I'm doing that. As I said, looking back the history, and from there, I want to extract the something. Why we are so successful still in, but this kind of conjecture still remains here. So central charge formula is invariant under monodromy action. Tk is x go to the exponential 2 pi I xk, and simultaneous transformation omega x0 to pi I kappa goes to the exponential minus kappa k omega naught x to pi I kappa. So this is just simply because xn plus 2 pi I kappa is, I haven't defined, but precisely 2 pi I 2 pi one summation. I'm sorry. Maybe I should write here. Summation k 2 pi I kappa k over log xk. This is a definition, and then do this monodromy transformation 2 pi I, and then this gives us log 2 pi I, and then 2 pi I divided here, and kappa extra kappa I, and they simultaneously act on this from the outside tk, and this cancels out. This is simply invariant. Then Now, why this is invariant? The interpretation is you know, that the homological mirror symmetry. So I'm trying to justify these definitions and also this conjecture in terms of homological mirror symmetry. So you know that the homological mirror symmetry says the equivalence of the one side is derived category of coherency, the other side the derived category of derived category of mirror side, and then from this category there is naturally the K group, naturally mapped to the K group, and from this side the object is Lagrangian subvarieties of X star. That means there is naturally X3 of X star Z. And then if these two categories are equivalent as a derived category, then there should be natural isomorphism of the K group to the middle dimension integral cohomology. So as I said, this side has a skew symmetric, Riemann-Roch pairing, and this side is natural Poincare duality gives us skew symmetric pairing. And then that's a homological mirror symmetry. And then if you look at the family of Calabi-Yau I constructed, and the xk equals 0, and then the monodromy around here is the action should be formulated as an action on the derived category. I don't know details. This side is very hard part, but at least this side we have a monodromy action. That's the linear action we have. And on the other hand, this one is coming from tensor of the minus kappa k, line bundle. That gives us, as a Fourier-Mukai factor, that gives us linear action on K group. And then this invariance says that this side is K of X, Tk, and this side is Tk of S side, X star side. And then if homological mirror symmetry is, this diagram must be commute. Naturally, we have this commutative diagram. And then combine this picture with this invariance of central charge here is this pairing central charge, or more precisely, this conjecture is coming from this homological mirror symmetry, isomorphism, homological mirror symmetry. So I'm saying that this is an abstract formulation of mirror symmetry, but eventually what we are observing mirror symmetry is this kind of hypersurface or complete intersections in complete, very explicit way. And then I'm saying that this central charge formula, well, maybe more recent terminology, gamma class, people says, and this is this comes from this isomorphism. Okay, so now I can conclude. So my claim, very nice, 90 minutes, the time is very nice. And if it were 60 minutes, I couldn't finish. So this is my last part. Claim is that assume central charge formula, assume central charge formula, or assume conjecture coming from central charge formula, and then we read from it phi equal mirror That's that kx. It's the x z with h even x. K group, or I mean the h even. This time I'm writing this. This R or Q, I'm not over here. So Q is left, so I should write Q. I'm not paying attention to the difference between Q and R here. H3 of H star of Q, and this comes from the H3 X star C of the point again. So homological mirror symmetry is some isomorphism which preserve this skew symmetric form this side, spherical symmetric form this side, compatible with this structure. And then I'm saying that this central charge formula, or the more explicitly, the basis from here, from this basis, describe this one. And then conjecture says that if make a basis here, and then coefficient functions is integral symplectic basis of the dual side. So somehow dualities are encoded in this single formula. That means the basis here and the coefficient function is the basis here. So that formula is automatically giving us the relation, the isomorphism between the correspondence here, the mirror. So that means the claim is that the and so if we assume central charge formula or conjecture which comes from there, then the mirror symmetry holds for hypersurface. P delta and delta star. So just I mean the sketch, the entire picture, just paying attention, everything encoded this formula or the conjecture here, and some inside here natural pairing and correspondence or isomorphism mirror is encoded with this correspondence base and this integral symplectic basis. That describes P here. And then
cases has been verified.
This one. It's I just say the no counter example so far. That's So sorry, that was a very honest way to answer. But these days, last year, I attended some conference, physics conference, and then they made this or I mean the hypergeometric system or the secondary polytope and those kind of things. So they are very skilled. And then the Keracon of the Keracon of 50 dimensional Keracon. They were able to describe and they were able to handle this series. And so calculating ground fit invariant and those kind of things we encountered all days. So what I did is dimension Keracon of 3 or 4. So I experienced for these cases, but just the problem is only for me. for physicists, they are very skilled using making computer code very efficiently, and then these days seems to be this kind of higher dimensional case we can calculate. So, I mean, in that sense, still this is conjecture, but I hope we can read something here. Thank you very much.
Enough time for questions. Any questions?
Well, I ask a very stupid question. How to see like K comes out with the formula in charge divided by 2pi.
Divided by,
No, that means integer that is sum with the K over 2pi is the nature number, nature. So how to see K divided by,
Why you want to divide by 2?
yeah.
why divided 2 pi I?
What's the point?
Good question. So, I mean, to get this one, to get this property.
So there should be a physical background for this kind of combination. I mean, integer that is sum with the K.
Yeah.
To me, it's nervous. Divided by 2pi is good.
Right. So something like that. I can't write this local system, but I mean, suppose there is a two second order differential, one second order differential operator, which have the local solution like this, and then, but if you want to have integral structure, so and if you look about the monodromy, and this is not the integral structure. So this gives us 2 pi I. So we have to divide 2 pi I. This kind of thing. Natural, very natural.
Because now everything is overseen, so of course you have the 2 pi I. But Calabi-Yau, that kind of symmetry should be found for it's a local field, that kind of thing. 2 pi in some sense, just transcendental.
Right. So to my intuition is something like this. We need 2 pi I here and somehow generalization. So integral to connect the integral basis here to the integral basis to the monodromy. So just this kind of generalization. Thank you.
Under the correspondence between this structure and this structure, the Calabi corresponds to the cone of the nilpotent.
Yes, yeah.
So on one side you have a movable
Movable,
which extends the Calabi.
Yeah.
Is there
Yes.
something on the femur side?
Yeah. So thank you for asking. So I have several examples where the movable cone mapped to the monodromy nilpotent cone so glued together, so large one. And there is a correspondence. So somehow there is a suppose a large complex structure limit around here, and then suppose another point. So it is inside the same modular space. So I haven't shown the example where two special boundary points. There is a case, so multiple boundary points inside the modular space, and then we have the sitting in lambda here, and we apply this structure here, and then from here, same thing, we can do the in lambda prime tilde or here. And then if we try to analytically continue from this local structure to here, and then this monodromy nilpotent cone naturally glued together to make a large cone. That's the movable cone, the mirror of the movable cone. I have several examples of this kind of phenomena. In general, very that's not so easy. Life is not so easy. And we need some more sophisticated formulation.
We already talked about this multiple mirror
Multiple phenomena. Yeah.
Actually, 20 years ago here.
Here. Are you?
I actually learned this from you.
Oh, yeah.
Yeah, I talked about this multiple mirror already. I guess maybe 22.
That means I'm sticking with this subject for long, and this time I'm looking back the history, and for me everything is important here, and I'm trying to extend beyond this one. Still, I mean, there's lots of work on the mirror symmetry. Thank you very much.
Can I just ask about the last sentence? So in the middle,
Yeah.
CCF implies NS.
Yeah.
Yeah. So of course CCF is a definition, right?
Yes.
So do you mean the conjecture?
Conjecture, yeah.
Conjecture.
Conjecture implies.
And the role of the central transform is to explain somehow it's part of the explanation.
Yeah, thank you very much. Conjecture. So conjecture part is main. Yeah, thank you.
No, well, let's thank you soon.
Thank you very much.
We are a very long policy. Yeah, so we don't. And also, for your reference, tomorrow night we will have a banquet for the conference. And also on Wednesday, after the second talk, we will have a group photo. So please, you are welcome to get all of this.
I think it's very nice.
Well, otherwise you just get that right. But class is so fast. No, sometimes I will just keep that's one thing that's very good idea to follow the steps. But for you to talk, You always did the class.